In today's video, we are going to cover the moons, planets, and asteroids in our solar system that have a real chance of space colonization, the capability for space travel to other galaxies, and the proposed implementation plan for setting up a permanent space settlement before our intergalactic journey takes off. Don't forget to hit the subscribe button to level up your knowledge with more great videos. To begin, the moon is the first most logical target due to its proximity to Earth and lower escape velocity. In celestial mechanics, escape velocity or escape speed is the minimum speed needed for an object to escape from contact with or orbit of a primary body. The moon is reachable from Earth in 3 days, has a near-instant communication to Earth with mineable minerals, no atmosphere, and low gravity, making it extremely easy to ship materials and products to orbit. Abundant ice is trapped in permanently shadowed craters near the poles, which could provide support for the water needs of a lunar colony. Since the moon has extreme temperature swings and toxic lunar regolith, it is argued by some that the moon will not become a place of habitation, but instead attract polluting extraction and manufacturing industries. Here are only a few materials on the moon which have been identified to make economic sense to ship directly back to Earth, which are helium-3 for fusion power and rare earth minerals for electronics. Instead, it makes more sense for these materials to be used in space or being turned into valuable products for export. In the space colonization framework, the moon will be transformed into an industrial hub of the solar system. Mars is the next planet worth noting, as both the United States and China have plans to send humans to Mars sometime in the 2040s. But these plans are not backed with hardware and funding. SpaceX is currently developing Starship, a super heavy lift, reusable launch vehicle with a vision of sending humans to Mars. As of November 2024, the company plans to send 5 uncrewed Starships to Mars in either 2026 or 2028 to 2029 launch windows. Mars is more suitable for habitation than the moon, with a stronger gravity, rich amount of materials needed for life, a day and night cycle nearly identical to Earth, and a thin atmosphere to protect from micrometeoroids. The main disadvantage of Mars compared to the moon is the 6 to 9 month transit time and the lengthy launch window, which occurs approximately every 2 years. Without in-situ resource utilization, Mars colonization would be nearly impossible, as it would require bringing thousands of tons of payload to sustain a handful of astronauts. If Martian materials can be used to make propellant such as methane with the Saboteur process, and supplies such as oxygen for crews, the amount of supplies needed to bring to Mars can be greatly reduced. Mercury is another planet that has been examined. Mercury is rich in metals and volatiles as well as solar energy. However, Mercury is the most energy-consuming body on the solar system to land for spacecraft launching from Earth, and astronauts there must contend with the extreme temperature differential and radiation. Once thought to be a volatile depleted body like the moon, Mercury is now known to be volatile-rich, surprisingly richer in volatiles than any other terrestrial body in the inner solar system. It is estimated that the poles of Mercury contain water, likely covered by hydrocarbons that would make agriculture possible. It has also been suggested that plant varieties could be developed to take advantage of the high light intensity and the long day of Mercury. Another option is to live underground, where day-night variations would be dampened enough that temperatures would stay roughly constant. The planet also receives 6.5 times the solar flux as the Earth and Moon system, making solar energy an effective energy source. It could be harnessed through orbital solar arrays and beamed to the surface or exported to other planets. This could make Mercury an ideal place to build and launch a solar sail spacecraft, which could launch as folded chunks by a mass driver from Mercury's surface. Once in space, the solar sails would deploy. Solar energy for the mass driver should be easy to produce, and solar sails near Mercury would have 6.5 times the thrust that they do near Earth. This could make Mercury an ideal place to acquire materials useful in building hardware to send to and terraform Venus. Vast solar collectors could also be built on or near Mercury to produce power for large-scale engineering activities such as laser-pushed light sails to nearby star systems. On the downside, a Mercury colony would require significant shielding from radiation and solar flares. And since Mercury is airless, decompression and temperature extremes would be constant risks. Venus and asteroid belts are another option, though the surface of Venus is extremely hostile. Habitats high enough above the atmosphere of Venus are fairly habitable, with temperatures ranging from 30 degrees Celsius to 70 degrees Celsius, and a pressure similar to Earth's sea levels at an altitude of 50 kilometers. However, besides tourism opportunities, the economic benefit of Venusian colonies is minimal. Asteroids, on the other hand, can provide enough material in the form of water, air, fuel, metal, soil, and nutrients to support 10 to 100 trillion humans in space. Many asteroids contain minerals that are inherently valuable, such as rare earths and precious metals. However, low gravity distance from Earth and dispersed nature of their orbits make it difficult to settle on small asteroids. This suggests that mining water and other volatiles in this region and transporting them elsewhere in the solar system, perhaps via the proposed interplanetary transport network, may be feasible in the not-so-distant future. This could make colonization on the Moon, Mercury, and main asteroid belts more practical. Next up is Saturn, Uranus, and Neptune. Although uninhabitable for living are the giant gas planets of our solar system, there have been proposals to place robotic aerostats in the upper atmospheres of the solar system's giant planets for exploration and possibly mining of helium-3, which could have a very high value per unit mass as a thermonuclear fuel. Helium-3, along with deuterium, could help us to drive a fusion economy, and some scientists believe that Saturn is the most important and most valuable of the three gas giants because of its relative proximity, low radiation, and large system of moons. Other scientists insist that Uranus is the likeliest place to mine helium-3 because of its significantly shallower gravity well, which makes it easier for a laden tanker spacecraft to thrust itself away. Furthermore, Uranus is an ice giant, which would likely make it easier to separate the helium from the atmosphere. The moons of Jupiter, Saturn, and Neptune have also been a large topic of discussion for colonization. Human missions to the outer planets would need to arrive quickly due to the effects of space radiation and microgravity along the journey. In 2012, Thomas B. Kerwick wrote that the distance to the outer planets made their human exploration impractical for now, noting that travel times for round trips to Mars were estimated at 2 years, and that the closest approach of Jupiter to Earth is often 10 times farther than the closest approach of Mars to Earth. New technologies such as nuclear thermal or nuclear electric engines combined with a plasma magnet sail have been suggested as significant advancements to improve spacecraft design. Now that we focused on the gas giants themselves, let's shift our attention to their moons. Jupiter's Galilean moons, Io, Europa, Ganymede, and Callisto, and Saturn's Titan are the only moons that have gravities comparable to Earth's moon. Radiation levels on Io and Europa are extreme, enough to kill unshielded humans within an Earth day. Therefore, only Callisto and perhaps Ganymede could reasonably support a human colony. Callisto orbits outside Jupiter's radiation belt, and Ganymede's low latitudes are particularly shielded by the moon's magnetic field, though not enough to completely remove the need for radiation shielding. Both of them have available water, silicate rock, and metals that could be mined and used for construction. Jupiter's moon Io is not ideal for colonization due to its hostile environment. The moon is under influence of high tidal forces, causing high volcanic activity. The moon is also extremely dry, and Io is the least ideal place for the colonization of the 4 Galilean moons. Despite this, its volcanoes could be energy resources for the other moons, which are better suited for colonization. The private Artemis project drafted a plan in 1997 to colonize Europa, involving surface igloos as bases to drill down into the ice and explore the ocean underneath, and suggesting that humans could live in air pockets in the ice layer. Additionally, in 2003, NASA performed a study called HOPE, the Revolutionary Concepts for Human Outer Planet Exploration, regarding the future exploration of the solar system. The target chosen was Callisto due to its distance from Jupiter and thus the planet's harmful radiation. It could be possible to build a surface base on Callisto that would produce fuel for further exploration of the solar system. HOPE estimated a round-trip time for crewed missions of about 2 to 5 years, assuming significant progress in propulsion technologies. Ganymede is the largest moon in the solar system, and Ganymede is the only moon with a magnetosphere, albeit overshadowed by Jupiter's magnetic field. Because of this magnetic field, Ganymede is one of only 2 Jovian moons where surface settlements would be feasible because it receives about 0.08 SV of radiation per day. Saturn has 7 moons large enough to be round, almost as large as the subscribe button that you should be hitting for more great content. In order of increasing distance from Saturn, they are Mimas, Enceladus, Tethys, Dione, Rhea, Titan, and Iapetus. The small moon Enceladus is also of interest, having a subsurface ocean that is separated from the surface by only tens of meters of ice at the South Pole, compared to kilometers of ice separating the ocean from the surface on Europa. Volatile and organic compounds are present there, and the moon's high density for an ice world indicates that its core is rich in silicates. Saturn's largest moon, Titan, is one of several candidates for possible future colonization of the outer solar system. though protection against extreme cold is a major consideration. Titan has hundreds of times more liquid hydrocarbons than all the known oil and natural gas reserves on Earth. These hydrocarbons rain from the sky and collect in vast deposits that form lakes and dunes, as Titan is just covered in carbon-bearing material and a megafactory of organic chemicals. Lastly, Neptune, the furthest planet from the Sun, has 16 known moons, of which Triton is the most discussed. Triton's surface shows signs of extensive geological activity that implies a subsurface ocean, perhaps composed of ammonia and water. If technology advanced to the point that tapping such geothermal energy was possible, it could make colonizing a cryogenic world like Triton feasible, supplemented by nuclear fusion power. Shifting to our second section of today's video, beyond the solar system, colonization targets might be identified in the surrounding stars. The main difficulty is the vast distance to other stars, and the distance between galaxies are on the order of 1,000,000 times farther than those between the stars, and thus intergalactic colonization would involve voyages of millions of years via special self-sustaining methods. To reach such targets, travel times of millennia would be necessary with current technology. At average speeds of even 0.1% of the speed of light, interstellar expansion across the entire Milky Way galaxy would take up to 1.5 of the Sun's galactic orbit period of 240 million years, which is comparable to the timescale of other galactic processes. Due to fundamental energy and reaction mass consideration, such speeds would be limited to small spaceships based on current technology. If, however, humanity would gain access to a large amount of energy, on the order of the mass energy of entire planets, it may become possible to construct spaceships with Alcubierre drives. The Alcubierre drive is a speculative warp drive idea according to which a spacecraft could achieve faster-than-light travel by contracting space in front of it and expanding space behind it, under the assumption that a configurable energy density field lower than that of a vacuum, that is, negative mass, could be created. The following Starship creations for intergalactic travel are plausible approaches with current technology. Let's discuss a few. A generation ship, for example, could travel much slower than the speed of light, with consequent interstellar trip times of many decades or centuries. The crew would go through generations before the journey was complete, so none of the initial crew would be expected to survive to arrive at the destination, assuming current human lifespans. A sleeper ship, where most or all of the crew spend the journey in some form of hibernation or suspended animation, would allow some or all to reach the destination. An embryo-carrying interstellar ship, much smaller than a generation ship or sleeper ship, could transport human embryos or DNA in a frozen or dormant state to the destination. As a result, obvious biological and psychological problems in birthing, raising, and educating such voyagers neglected here may not be fundamental. Next up is a nuclear fusion or fission-powered ship, which could achieve very high velocities, permitting one-way trips to nearby stars with durations comparable to a human lifetime. Another example is a Project Orion ship, which is a nuclear-powered concept proposed by Freeman Dyson, which would use nuclear explosions to propel a starship. A special case of the preceding nuclear rocket concept with similar potential velocity capability, but possibly easier technology. Laser propulsion concepts using some form of beaming of power from the solar system might allow a light sail or other ships to reach high speeds, comparable to those theoretically attainable by the fusion-powered electric rocket above. These methods would need some means, such as supplementary nuclear propulsion to stop at the destination. But a hybrid that involves light sails for acceleration and fusion electric for deceleration might be possible. Another example is uploaded human minds or artificial intelligence that may be transmitted via radio or laser at light speed to interstellar destinations, where a self-replicating spacecraft could have traveled subliminally and set up infrastructure and possibly also brought some minds. To end off today's video, once you hit the like button and subscribe, let's discuss the proposed implementation of space colonization. Building colonies in space would require access to water, food, space, people, construction materials, energy, transportation, communications, life support, simulated gravity, radiation protection, migration, governance, and capital investment. It is likely the colonies would be located near the necessary physical resources. In space settlements, a life support system must recycle or import all the nutrients without crashing. The closest terrestrial analog to space life support is possibly that of a nuclear submarine. Nuclear submarines use mechanical life support systems to support humans for months without surfacing, and this same basic technology could presumably be employed for space use. Importantly, space manufacturing could enable self-replication, Some consider it the ultimate goal because it would allow an exponential increase in colonies while eliminating cost to independence on Earth. It could be argued that the establishment of such a colony would be Earth's first act of self-replication. Intermediate goals include colonies that expect only information from Earth, such as science, engineering, and entertainment developments, and colonies that just required periodic supply of lightweight objects such as integrated circuits, medicines, genetic material, and tools. From a population standpoint, it is estimated that a population of 150 to 180 individuals would permit a stable society to exist for more than 60 to 80 generations, equivalent to 2,000 years. Jean-Marc Salotti proposed a method to determine the minimum number of settlers to survive on an extraterrestrial world, and it is based on the comparison between the required time to perform all activities and the working time of all human resources. For Mars, 110 individuals, for example, would be required. Over the last 2 space videos that have been put out, I want to thank you for taking the time to explore the reasoning behind why space colonization is essential for the survival of humanity, the undeniable challenges we would face, the moons, planets, and asteroids we could colonize in our solar system, the potential for intergalactic travel to other galaxies, and the proposed implementation strategy of successful space colonization. Have a great rest of your day, everyone, and I'll see you in the next video. Thanks.